Now, in the previous session, we took the psi function and we assumed that the potential V was time independent, so it was only a function of the position x, and then we were able to split up the psi function into two terms, u, which was a function only of position, of x, and f, which was only a function of time. And we had on the left hand side, if you remember, terms involving only the position, and on the right hand side we had terms involving only the time, and the only way those two could be equal is if they both equal to the same constant, and we call that constant E. E for energy, but that's not clear yet, showing that E is of an energy nature this session. Alright, so now we wrote out the equation. I've written out it again here just to reminder. Here is the U term, the position dependent term, and it's usually called the time independent Schrödinger equation because time does not come into this equation, right? So it's the second differential with respect to position x plus VU equals EU, right? And that is in fact an eigen equation. It's in that form, but it's usually referred to as the time independent Schrödinger equation, and we'll be dealing with this kind of equation a lot in the coming lectures, and not just sessions. Okay, whole chapters on this equation. You're given a particular V, and then you're to solve for the eigenvalue, what energies are, energy levels, for example, are possible, and what are the eigenfunctions, in other words, the wave function, the U here, right? Okay, so what about the time dependent part, the F? Well, it will have this form. Remember before we had a 1 over F here equals E, the constant, so bring that 1 over, bring the F over, and you'll get this form. Now that's a pretty simple first order differential equation. By the way, wave mechanics, dealing with Schrödinger's equation, it pretty well boils down to differential equations, just solving differential equations. And that, after all, was what Schrödinger was an expert in at the time when he created his famous equation, Schrödinger's equation, because that was his specialty. His differential equations, and a branch of differential equations are wave equations, and he knew a lot about wave equations. So he was the right guy at the right time to find the wave equation for de Broglie's waves, these wavicles, particles with wave-like properties. And he was the right guy. Anyway, so you can solve this pretty readily. It's just a first order differential equation, and this will be its solution. I assume you've done enough calculus to be able to solve such a DE differential equation. Here's the solution. So whatever your U is, when you solve your time independent Schrödinger equation of this form, the second differential with respect to x plus VU equals EU, when you solve that equation, you get values for U, the space dependent part of your wave function, your psi. Well, just whatever it is, put it in here, and you know your F is of this form, so it's exponential minus IET divided by h bar, right? It'll be of this form. Now, can you go back a bit? Remember that how do you interpret, well, Born, B-O-R-N, Born's interpretation. What does the psi function mean? Well, he interpreted it if you square it. So the psi function for him is just an amplitude. Remember, an amplitude is physical. Well, it's something in physics. When you square it, you get something that has physical reality. In this sense, a probability density. So that's what the PD stands for. So, according to Born's interpretation, that he eventually, after many decades, got a Nobel Prize for, he interpreted the square of this amplitude as a probability density. So now if you square this thing, this exponential term disappears, and you're just left with the modulus of u squared. Okay. Now that is not, the mod of, the absolute size of squared of u is not time dependent, right? It's time independent. So in other words, the probability density, whatever it is, will remain constant in time because of this. This does not depend on time. Okay, so the probability density is time independent, right? And so the psi function here, when the probability density remains constant, that psi function, or state if you like, is stationary, meaning not changing in time. It's a stationary state, right? It's a stationary state. Okay. All right. Well, now with that out of the way, let's talk about this constant e. This e here. Well, now for the moment it's just a constant in a differential equation. But in physics, what does it take on a meaning of some sort? What is this constant that we've called e? I mean, we could call it c or k or anything, right? Call it e. Well, to give some clues on its nature, what is this e? Let's take the wavicle, this de Broglie type particle with wave properties. If you de Broglie yourself, you might think of this wavicle as sort of like a surfboard riding on a wave. So the wave guides the particle, it pilots the particle, but that idea has been strongly criticized by a lot of people, and later on, even in this chapter of the book, Davies' text, we will come across multi-particle systems which also have a wave function for more than one particle, and then you're getting into more than 3 dimensions, and so interpreting the psi function simply as a 3-dimensional wave in 3D space, like a real wave, well, it starts getting very dubious, right? So like interpretation of quantum mechanics, there's a lot of discussion. What's going on here? All right. Okay, so let the wavicle be free. In other words, there's no potential applied to it. There's no electric field. There's no magnetic field. There's no gravitational field. There's no field at all. It's just free to do what it likes. It just roams free. So in other words, the potential on it is 0. Okay. We're doing this just to simplify things. All right. Well, here's our time-independent Schrödinger equation, right? With our E. Now, if we're assuming this wavicle is free, there's no potential. The V here is nothing, so this term disappears, and so we've just got this, which is this. So you can rewrite this time-independent Schrödinger equation as this. Okay. Now. You remember when we derived the Schrödinger equation in the first place? I've done it twice now. Our wave function had this kind of form, sort of e to the I, and then we had in brackets like kx plus omega t or something. So we had something of this form. Now u does not depend on time. Okay, so the time part of this general wave function, that drops away. We're just left with the x part, right? The spatial part. So it'll be of something ikx. And remember, this k here was the wave number. That was 2 pi divided by lambda, and lambda was the wavelength of the de Broglie wavicle, particle with wave-like properties. So this k here is the wave number. Remember that? All right. So the solution, now this is a second order differential equation, right? So assume again you have enough calculus to be able to solve this fairly readily. So the solution u to this equation will have something of this form, right? And so if you differentiate this twice, you'll get an ik times ik at the front here, so you get minus k squared. You got a minus here, so you'll get k squared u, and therefore the minus k squared equals this. So k squared equals, you're simplifying things a bit, 2me over h bar squared. But so bring the h bar squared over here, divide by 2m, and you're left with e is h bar squared k squared divided by 2m. Right? But h bar k is the momentum of the wavicle. Right? That's de Broglie's famous equation. Well, rewritten slightly, but it's relating the momentum to the wavelength. Remember, k, the wave number, is 2 pi over lambda. Right? So P equals hk. That's de Broglie's famous equation for relating the momentum of the wavicle and its wavelength. Right? So h squared k squared is just p squared. Well, you got p squared over 2m. Well, that's kinetic energy. Right? That's the famous classical kinetic energy formula. But E equals that. All right. Therefore, this constant E is takes the form of energy.